Welcome pre-cal students to the homework help video for this assignment right here on the screen in front of you. Let's go ahead and get started right away and hopefully get your questions answered on the math that you have. On page 144, the first section we're looking at says for each function, construct and simplify the difference quotient. Okay, let's go ahead and start with this problem right here. We should know by now that the formula we're going to use is f of x plus h minus f of x all over h. Okay, so with that in mind, let's go ahead and get started. The first thing that I'm going to be concerned about is this right here, f of x plus h. So wherever there's an x, I'm going to put x plus h. So negative 3/5, and then parentheses, and then x plus h, and then plus 10. So there we go. And then minus what? F of x. And all of this is f of x equals this. So I'm going to put parentheses, negative 3/5 x plus 10. And of course, all that's over h. I'm not going to worry about that until the end, okay? Let's simplify. Take your negative 3/5 and multiply it through. Negative 3/5 times x and negative 3/5 times h. Bring down your positive 10. Take this negative sign and multiply it through. Negative times a negative is a positive 3/5 x. Negative times a positive is a negative 10. And of course, all that is over h. Now look what happens. I have a negative 3/5 x and a positive 3/5 x. I have a positive 10 and a negative 10. So the only thing I'm left with is negative 3/5 h, and don't forget it's all over h, so your h's cancel out, so your answer is negative 3/5. So you found the difference quotient, all right, for this function right here. Let's try another one, number 51. Remember our formula, of course, is f of x minus h minus f of x, and that should be a plus sign right here, all over h. Okay, here we go. Everywhere there's an x, I'm going to put x plus h. So 3, then here's an x, parentheses, x plus h, and then minus 5. And then the next part of the formula says minus f of x, so minus parentheses, and f of x equals 3x minus 5. So I'm going to put 3x minus 5 all over h, and I'll put that h in later. Okay, let's simplify the numerator. 3 times x is 3x, 3 times h is 3h. Bring down your negative 5, take your negative sign and multiply it through, negative 3x and positive 5. And now look what happens. Your positive 3x cancels with your negative 3x, your negative 5 cancels with your positive 5, and you're left with 3 over h, or excuse me, 3h over h. Your h's cancel, and so the difference quotient is 3. Okay, pretty cool. All right, 2 more of these types of problems left. Let me get a drink here, and then we'll continue on. Here we go. All right, number 55. All right, number 55. Let's go ahead and save us a little time. We'll pull this formula over right here. And there we go. All right, now, first of all, everywhere there's an x, we're going to put x plus h, f of x plus h. So I would have 4 plus, then a 5, then absolute values, x plus h. And then minus f of x, so minus, then put a parentheses, then this whole expression, 4 positive 5, absolute value, x, close your parentheses, and of course this is all over h, and I'm not going to worry about putting that until the end of the problem. Okay, there's really not a lot of simplifying you can do. I would not multiply the 5 through the absolute values. I would leave it 4 positive 5 absolute values x plus h, and then the negative sign, multiply it through. Negative times a positive 4 is a negative 4, negative times a positive 5 is a negative 5, absolute value of x. Okay, and now of course your positive 4 and your negative 4 cancel, And so those are going to be totally gone. We'll see if we can get rid of them real quick there. And then we'll slide this over. So there we go. That is your answer, of course, all over H. And that's totally acceptable. There's nothing else you can do, students, okay? That's as far as you can simplify that. And that's an expression in which on any curved graph, whatever you have, if you have two ordered pairs here and here, you can find the average rate of change by simply knowing what the x value is here and then what the difference is between the x value over and between what this x value right here would be. Okay, so this is definitely helpful. All right, let's go ahead and take a look at one more problem here in this section, number 59. Okay, let's take a look at number 59. Let's see if we have the, hold on one second please, there we go. Alright, there's the formula we've been using. So let's go ahead and take a look at this. Everywhere there's an x, I'm going to put x plus a. So here's an x right here. X plus h minus 4 over x plus h plus 3. Okay, so that would be f of x plus h, and then minus x minus 4 over x plus 3. And of course, when we're all done, that's going to be all over h, and we'll worry about that in the end. Okay, all right, now it looks like to me we're going to have to find a common denominator, and I believe the common denominator, if I'm not mistaken, would be x plus 3 x plus h plus 3. That should be the common denominator. And so let me quickly make a note of that. If I get my mouse to work here. And it looks like it's quit working, so we'll use this pen right here very quickly. All right, let's go ahead and do this. And there we go. Now we've copied that. Okay, so there's my common denominator for these two fractions. It looks like I'm going to have to get a common denominator and then put these two fractions together. Now remember how to do this. What do I have extra here I don't have here? X plus 3, and you bring down your numerator. So bring down your numerator and also put up here x plus 3. Now what do I have extra here I don't have here? Well, this right here, x plus h plus 3, and then bring down your x minus 4, x minus 4. Now we'll quickly do some multiplication and we'll see what we come up with. Okay, so here we go. On top of this fraction right here, I would have x times x is x squared plus 3x plus hx plus 3h minus 4x minus 12. Now what I did is I took this x and I multiplied it through, then this h and I multiplied it through, and this negative 4 and I multiplied it through, just to simplify. Okay, now I'm feeling like I might run out of room here, so I'm going to slide this over just a little. Let me get a drink here. Okay, so there we go. And now minus, now be careful, we're going to subtract this whole expression, so I'm going to keep all of this in parentheses, okay, because this negative sign goes for everything up here. Be really careful about that, okay, students? So take your x and multiply it through. X times x would be x squared, x times h would be xh, x times 3 would be 3x, and then negative 4, negative 4x, negative 4h, and then negative 12. And I think, let me make that a little bigger, negative 4h, negative 12. Now because this negative sign here, all of your signs in here are going to change. Okay, please don't forget that. So all of your signs will change inside the parentheses. So this was a positive x squared, now it's negative. Okay, this is a positive x8, so now it's going to be negative. This is a positive 3x, now it becomes negative. This is a negative 4x, so we'll make it positive. Then we'll make this positive, and we'll make this positive. Okay, and don't forget, all of this is still over, unfortunately. Your common denominator still which is this right here. Now I'm not going to worry about that common denominator right now. I'm worried about simplifying all of this. For example, watch what I do here. See this x squared? And there's a negative x squared right here. They cancel out. Here's a positive 3x and a negative 3x. So those are going to cancel out. Here is a positive hx and a negative hx. Here's a negative 4x and a positive 4x. Here is a negative 12 and a positive 12, and look at that. Wow, 3h plus 4h would give us 7h. Let me get a new page here. So what we have is 7h all over your common denominator, which is this right here. And don't forget, that's still all over h. Okay? Now please watch carefully what we do. We take our top fraction and we divide it by our bottom fraction. Now here's your top fraction divided by your bottom fraction, which is really h over 1. Okay? So I'm taking my top fraction and I'm dividing it by h over 1. Now remember, when you're dividing fractions, you really multiply and you flip these two fractions around. So now, if you'll do that correctly, your h cancels with your h, and 7 times 1 is 7 over, and here's your final answer, 7 over x plus 3 times the quantity x plus h plus 3. That was a tough one, but that's how you would simplify that problem. Okay, well, let's continue on. That was 4 problems using difference quotients. Okay, let's continue on. Next, we're looking at a section where we're doing composition of functions. Okay, composition of functions. Now, here they want us to take f of g of negative 1. So remember, f is first, so we start with our f function, and everywhere there's an x, I put a big parenthesis. So 3, big parentheses, plus 1. Now, what letter came next? G. So I pick up g and I put it inside this parentheses. So x squared minus 2x minus 6. Well, let's simplify. Take your 3 and multiply it through. 3 times x squared is 3x squared. 3 times negative 2 is negative 6x. 3 times negative 6 is negative 18 plus 1. So I would then get 3x squared minus 6x minus 17. And then remember, it wasn't good enough to just find the composition. They want us to put negative 1 in for x. So 3 parentheses negative 1 squared, negative 6 parentheses negative 1 minus 17. So you end up with a positive 6, a negative 17, a negative 1 squared is a positive 1 times 3 is a positive 3. So a positive 9 minus 8 is or a positive 9 minus 17 is going to give you a negative 8 for number 61. All right, number 63, we're doing h of f. Composition h of f. So our first letter is h, so we take our h function, and everywhere there's a parentheses, everywhere there's an x, we put a pretty big parentheses, so x cubed, parentheses cubed, and then we substitute f in. So I would have 3x plus 1. Now, if you feel like taking 3x plus 1 times 3x plus 1 times 3x plus 1 and writing this parentheses out 3 times, feel free to do that. I do not feel like doing that, and I really don't need to, because they're not asking me to. They just want me to find negative 1, h of f of x of negative 1. So where there's an x, I'm simply just going to substitute a 1 and then put plus 1 and then raise it to the third power. Well, 3 times 1 is 3, plus 1 is 4, so I have 4 to the third power, and that's going to give you 64. Okay, 64. All right, very good. Let's continue on. Now they want us to find g of f of 5, g of f of 5, so my first letter is a g, so I take my g function, and everywhere there's an x, notice I'm putting a parentheses, pretty big parentheses. And then my next letter is f, so I'm going to substitute f in. Now, if you want to go ahead and simplify, you can. I think I'm just going to go ahead and put my 5 in for x right now. So I would have 3 times 5 plus 1, all of that to the second power, minus 2, parentheses, 3 times 5 plus 1, and then negative 6. So here we go. 3 times 5 is 15. 15 plus 1 is 16. And then 16 squared, I don't have my calculator with me, that'd be what, 96, 256. So 3 times 5 is 15, plus 1 is 16. 16 squared is 256. And then here we have 3 times 5 is 15, plus 1 is 16. So all of this right here is 16 times negative 2, that's a negative 32, and then minus 6. All right, and so if we do this correctly, we should come up with negative, let's see, negative 38 minus that would give you 218, which is the correct answer. Okay, 218. All right, one more of these. Again, we're practicing composition of functions. F of h of negative 3. My first letter is F, so everywhere there's, I'm going to take my F function. Everywhere there's an X, I'll put a pretty big parentheses. And then next is h, so I'm going to substitute h into that parentheses. There we go. Now we could simplify first if we wanted to. I'm just going to go ahead and put negative 3 in for x. Now notice how I use parentheses where there's an x. I just don't want to put negative 3 to the third power. It's negative 3 in parentheses to the third power. Now, negative 3 times negative 3 times negative 3 does give me a negative 27. And then 3 times negative 27 is a negative, let's see, 81. Plus 1 would give me a negative 80. Okay, so we just practiced their composition of functions and then evaluating the composition at a given number. Okay, doing really well, moving right along. We're almost finished here. Let's take a look now at numbers 1 through 6, I believe, and we're just simply going to look at the graph and decide whether we have x-axis symmetry, y-axis symmetry, or origin symmetry. Okay, so let's take a look at number 1 here. Number 1. Okay, when we look at number 1 here, we can kind of see it's wrapped around the y-axis like this. Looks pretty, I mean, we're just going by the naked eye, but it looks pretty symmetric to me. So yes, this graph has y-axis symmetry. It does not have x-axis symmetry. It's not wrapped around the x-axis, that's for sure. And it doesn't have origin symmetry either. For example, if I had an ordered pair here that was like negative 5, 3, which that looks like it's right, then that means that the ordered pair positive 5, negative 3 would have to exist, and that's just not the case. Okay, so we do not have origin symmetry, nor do we have x-axis symmetry. We do have y-axis symmetry. Okay, let's take a look now at number 2. It's going to end up being the exact same thing again. We definitely don't have x-axis symmetry. It's not wrapped around the x-axis. However, if you look at this graph, it is wrapped very well around the y-axis symmetrically. Okay, so we do have y-axis symmetry. Now, as in terms of origin, that's going to be the hardest one for y'all to decide. Okay, but remember, take for example this ordered pair right here. We went over so far and down, so we know it's got to be a negative so far and then up, and that just doesn't exist. It means this poor ordered pair here, it was a positive x and a negative y. Isn't that right? We went over x and down y. Well, now try to reverse that and go negative x and up y. You would be about right here, and that point does not exist. Okay, another way to look at that, how about this point right here? This point is negative x, positive y, and so if we really had origin symmetry, which we don't, but if we did, we'd have to have a positive x and then a negative y about right here. Okay, and we don't have that at all. We do not have origin symmetry. One more way to help with origin symmetry if you're confused. X-axis and y-axis are pretty easy, but if you're confused on the origin, pretend you had a sheet of paper and you folded it in half right here on the x-axis, and then after you folded it over in half, then you folded it again on the y-axis, and if the entire graph fell on top of each other, then you would know you had origin symmetry. And that's another, hopefully, an easier way to understand that. Okay. All right. Number 3. Well, we definitely don't have y-axis symmetry. It's not wrapped around the y-axis. We do have x-axis symmetry. That's obvious. It's wrapped around the x-axis. And guys, there's no way we have origin symmetry. No way. This ordered pair here, think about it. It's over negative x and up positive y. So let's change that. Let's go positive x and negative y. And does that point right there exist on this line? Not at all. No way. And so we do not have origin symmetry. Okay. All right. Let's take a look at number 4. All right. Now on number 4, it's obvious we don't have y-axis symmetry because it would have had to have gone like this and then back up again like that. And it's obvious we don't have x-axis symmetry because it would have had to come down and hit here and then go like that. So we don't have that. We might have origin symmetry. It's looking pretty good, actually. Think of this ordered pair here. You're over then up, so over and then down looks pretty good. Let's take a look at this point right here. You're over a little bit and then up, so over a little bit and then down. And plus, if you were to fold this, think about it. If you were to fold this on top of the x-axis, fold it on top, it would come when you fold it. If you were to take this like it was a sheet of paper and fold it right here, then this graph right here would now be down here like this. And then if you folded it right here on this y-axis, this graph would fall perfectly on top of this graph. I hope that makes sense. And so yes, we definitely have origin symmetry. Okay. All right. Number 5. Let's take a look at number 5. Now, there's no way we have y. Let me show you why we don't have y-axis symmetry, guys. Look, excuse me for yawning. If it comes down like this, then that means it's also got to do this over here. Okay? I mean, in order for this thing to have y-axis symmetry, it has to be exactly the same, like this. If it's going to do this over here, then it's got to do it over here like that. And if it comes over here and does that, it's got to do it over here. It has to be exact on both sides of the y-axis, okay? And we don't have that. Same thing on the x-axis. I mean, look, if it's going to come down and go like this, then it's going to have to come out and go like that here so that it matches this perfectly. So we do not have y-axis or x-axis symmetry. Now, origin is looking pretty good, to be honest with you. I mean, this ordered pair right here is over so far and up, so then you go over so far and down, it hits that point there. Let's try this point here. We're positive and positive. Let's go negative and negative. Yep, it would hit right here. How about this ordered pair right here? That's positive, positive. So we'll go negative, negative. It hits right here. Yeah, it's looking really good. Plus, if you were once again to take this and pretend it was a piece of paper and fold it right here on that x-axis, if you did that successfully, the graph would look like, it's going to be hard to draw, but the graph would look something like this if you folded it on the x-axis. And then if you folded it on the y-axis, look at this. This graph right here, this part would fall right on top of this, and this part would fall right on top of that. It works perfectly. We do have origin symmetry. Okay, we do have origin symmetry. All right, number 6, and we're finally finished. Number 6. All right, let's take a look at this. Now, if you were to fold this on the y-axis, on the x-axis, it would fall right on top of the other side. If you were to fold it right here, like it's a piece of paper, this graph would fall right on top of this. So we definitely have y-axis symmetry. If you were to fold the paper right here on the y-axis, this part right here would fall right on top of this part over here. So we definitely have y-axis symmetry. Okay, we have all of that. And then if we were to fold it twice, fold it over the x, well, the graph would fall like this, and this would be gone. And then if you were to fold it on the y-axis, this part right here would fall right on top of this part over here. So we definitely have origin symmetry. And another way to check that if you don't like that method is, look, see this point here, negative and up positive, go positive and down negative, it hits it there. How about this point right here? It's positive, positive, so we'll go negative, negative, it hits right here, so on and so forth. Okay, so we do have origin symmetry, x-axis symmetry, and y-axis symmetry, all three in this problem here. Okay, in the next section, let me turn back to the proper page here real quick. And I apologize for not being there. This next section, I believe, is asking you to test for symmetry, I believe. Let me turn over there and look. Okay. Determine whether we have symmetry with respect to the x-axis, y-axis, or the origin. Okay, no problem. Let's take a look at number 15. Everywhere there's an x, I put a negative x. And obviously, that's not going to work. 5 times negative x is negative 5x minus 5y equals 0. I do not get out the original equation. Now I'm going to substitute negative y everywhere there's a y. So 5x minus 5 parentheses negative y equals 0. Well, negative 5 times negative y would be 5x plus 5y equals 0. Okay, and that is not the original equation. And so now everywhere there's an x, I'm going to substitute negative x, and everywhere there's a y, I'm going to substitute negative y. And let's see what happens here. 5 times negative x is negative 5x. Negative 5 times negative y is positive 5y equals 0. Now let's go through and change all of our signs. Negative 5x becomes positive 5x. Positive 5y becomes negative 5y. And of course 0 stays 0. So did I get out the original equation right here when I simplified? Yes, I did. So 15 does have symmetry with respect to the origin. Well, let's take a look at number 17 now. Number 17. And let's see what we got here. Everywhere there's an x, I'm going to substitute a negative x. And I think this is pretty obvious what's going to happen. I mean, anytime you square a negative x, you get a positive x squared times 3. So you end up with 3x squared minus 2y squared equals 3, which is the original problem. So y symmetry checks. Very good. Now let's check for x-axis symmetry. So everywhere there's a y, I'm going to substitute a negative y. And I think you can see very quickly this is going to work. I mean, anytime you take a negative y squared, it's a positive times the negative is going to give you what you started with, negative 2y squared. So yes, x symmetry checks. And then, of course, if you put a negative x in for x and a negative y in for y, you're going to see everything does simplify back to the original problem. All right, if we square a negative, we get a positive 3x squared. If we square a negative y, we get a positive times a negative 2 is a negative 2y squared equals 3. So in this case, all three did exist, okay? All three. All right, number 19. Let me get a drink here. Okay, let's go ahead and check for y-axis symmetry first. We'll go ahead and put a negative x in. Y equals absolute value 2, negative x. Now you got to kind of think here a little bit and reason, okay? I mean, 2 times negative x is negative 2x. But then we know out no matter what. Look, this is the exact same thing because 2 times x, whatever you get out, comes out to be a positive number. Well, I don't care if there's a negative 2 here because negative 2 times any number is going to give you a negative number. And when you take the absolute value of it, it's going to come out positive. So look, those are identical. And so yes, we do have y-axis symmetry. Yes. Okay, now let's check for x-axis. We'll put a negative y in for y. And there's really nothing we can do here. I mean, that I can see. A negative y in parentheses, just a negative y equals absolute value of 2x. Get y by itself, so we're going to go through and change all the signs of each term. And so this is one term right here. So we change the sign on the outside to negative, and we do not get the original problem. And then lastly, we'll check for origin, and it's not going to work. We're going to have a negative y for y, and then over here we'll have 2 parentheses negative x, and we already know that this whole right side over here simplifies to this right here. We learned that earlier in this problem when we saw that y-axis symmetry exists. There's still a negative y here. Now go through and change your signs. Y equals negative absolute value of 2x. So it does not work. You do not get out the original problem. So the only symmetry we have is y-axis symmetry. All right, number 21. All right, here we go. Now, I'm going to go a little faster on these. I think we really should be understanding this. If we put a negative x in, do you not see how if I put a negative x to the 4th power, I just get out a positive x to the 4th, and so nothing changes? We really should start to see that by now, students. I'm not trying to be impatient with you, but you really should see that. I mean, look at it like this. Everywhere there's an x, I'm going to put a negative x. And if I take negative x times negative x times negative x times negative x, that's positive x to the 4th times 2. Then I get out 2x to the 4th, and nothing else changed because I didn't change anything. So when I put negative x in, I did get out the original problem. And so that means I do have y-axis symmetry. Now let's check for x-axis symmetry. I'll think about this. Everywhere there's a y, I'm going to put a negative y. Now here's my y, and it's a negative y squared. Well, look, guys, if I take a negative y times a negative y, we all know it's going to give me a positive y squared. And nothing over here changed. And so everything comes out, when you're done simplifying, it comes out to the original problem. So I definitely have x-axis symmetry. And by the way, I'm also definitely going to have symmetry with respect to the origin, because look, if I put a negative x in here and a negative y in here, I mean, this comes out to be positive, the 3 doesn't change, this comes out to be positive times 2, nothing changes. Okay, so we do have symmetry with respect to the origin and the y-axis and the x-axis. Okay, now this one here should be pretty obvious. I mean, look, let's start off checking for x-axis symmetry, okay? Where there's a y, I'll put a negative y. Now look, if you're taking a negative y to the 3rd power, negative y times negative y times negative y is a negative y cubed. Times 3 gives you a negative 3y cubed. And then, of course, what you want to do then is go through and change all the signs so you have a positive 3y cubed, and when you do that, it does not match the original equation. It does not. Let's check very quickly for y-axis symmetry. Okay, y-axis symmetry. Well, everywhere there's an x, I'm going to put a negative x. Now think about this. 4 negative x to the 3rd power. Well, negative x times negative x times negative x is negative x cubed, times 4 is negative 4x cubed plus 2. Nothing changed over here. We didn't make any substitutions. You do not get out the original problem. Not at all. So we do not have y-axis symmetry. Now let's check for the origin real quick. Where there's a y, I'm going to substitute a negative y. And where there's an x, I'm going to substitute a negative x. Now watch what happens here, okay? Please watch this. All right, negative y to the third power is negative y cubed times 3. So negative 3y cubed equals, okay, negative x to the third power is negative x cubed times 4. That's negative 4x cubed. And then positive 2. 2 is not going to change at all. We just bring that down. Now look, when you take this negative 3y cubed to make it positive, go through and change all the signs. Well, if you go through and change all the signs, that's now positive. That's now positive, and that's negative, and that does not match the original problem. No way, not at all. And so we do not have symmetry with respect to the origin either on this problem. So all three failed. All right, let me get a drink here real quick. Now we should be able to figure this pretty quickly. Look, if you put a negative x in for x, I mean, come on, students. Negative x times y is just negative xy. Go through and change the sign of each term. Positive xy equals negative 12. It's just not going to work. And then if you put a negative y in, it's not going to work either. You would have x times negative y equals 12. X times negative y is negative xy equals 12. And then, of course, change the xy to a positive, change the 12 to a negative, and it does not match the original problem. So no, we do not have x-axis symmetry or y-axis symmetry. Both of them failed. However, origin is going to work because you put a negative x in for x, you put a negative y in for y, negative x times negative y, negative times negative is a positive, xy equals 12. So yes, 25 does not have x or y-axis symmetry, but it does have origin symmetry, okay? All right, and now moving on to our last three here. These are pretty easy. You'll enjoy this. So we're going to make a table for every single one of these. I'm going to put x-axis symmetry, y-axis symmetry, and then origin symmetry, because they are asking us, if you'll read the directions, they want us to find the point that is symmetric to the given point with respect to each one of these scenarios here: x-axis, y-axis, and origin. Okay, so let me copy this, and here's what they mean. Remember I told you if you have x-axis symmetry and you have a point like negative 5, 6 on the graph, then you know for sure you're also going to have negative 5, negative 6, because whenever you have x-axis symmetry, that means the sign of the y will change. Now if you have y-axis symmetry, then the sign of the x is going to change. So if you have an ordered pair 5, negative 5, 6, and you want to know the ordered pair that goes along with this so that you have y-axis symmetry, well, it would be a positive 5, the 5 changes, and the 6 does not. Okay, you change just the x value. Over here with x-axis symmetry, you change just the y value. Now for the origin, you change both. So you would have a positive 5 and a negative 6. Pretty simple, okay? Let's do a couple more of these and we're done. All right, now let's go ahead and find the ordered pair that would give you x-axis symmetry. You change the sign of the y value, not the x. So negative 10, 7. Now let's go over here and let's find the ordered pair with respect to this ordered pair here that would give you y-axis symmetry. Well, if it's y-axis symmetry, you change the sign of the x. So instead of negative 10, negative 7, it's 10, negative 7. And then for the origin here, if you have origin symmetry, that means both of these signs would be changed. So it would be a positive 10 and a positive 7. One more of these and we're finally done. Number 31. Here we go. X-axis symmetry, change the sign of the y, 0, positive 4. Y-axis symmetry means change the sign of the x. You really can't change the sign of 0, so we just leave it 0, negative 4. Okay, origin symmetry, you change the sign of both numbers, so you leave 0, 0, and you make negative 4, positive 4. And that's it. I hope this homework help video has been a help to you. Please call or email if you have any questions at all.